Okay, so why don't we go over some example problems? What you guys should be seeing on my screen right now is all the packets that I had uploaded. All the packets I had uploaded to my website. I'm just going to go through some of these. And if y'all have questions, I need you to like raise your hand or just unmute yourself or type in the chat, do something to make sure that you get your question asked. So I have these open on my screen in the order that I uploaded them. There was this kinetics practice thing. This is all multiple choice questions that you do not know how to do yet. So we can skip this one for now. The next packet was a kinetics multiple choice. We can probably do some of these. There were some free response questions. And I think we'll be able to work through some of those. There was super problems and a practice quiz that, yes, this video, I just remembered to start recording it. So yes, I just recorded it. Okay, so I'm just going to go through and I'm just going to work some, I don't know, some random example problems. Why not? If you guys have questions, please, please, please jump in and ask, okay? So let's look at this multiple choice one. Right away, this first question, I have this chemical reaction, and then here's my rate law. It's a differential rate law. The question asks me, what is the order of the reaction with respect to I? That's really simple. That's just the exponent that the concentration of I is being raised to. It looks like that exponent is a 1 to me. So number 1, here the answer is A. Okay. According to the rate law, an increase in the concentration of hydronium. Does anyone know what hydronium is? Mr. Roberts asking a question. Do I want the answers to the packet on a document that you can just email to me? I do not care right now. I'm not going to take this packet up until after spring break. So if you want to do it on paper and then take pictures of it and email it to me, or share it in the Google Classroom at that time, you can do that. If you want to keep a running doc, totally up to you. Whatever you think will be easier for you in the future to turn it in to show me that you did it. Okay, someone tell me what hydronium is. Someone unmute yourself and be brave and tell us what.
It's H3O.
All right, excellent. Thank you, Mr. Sanford. Hydronium is H3O. So look at the rate. The rate does depend on the concentration of H3O. This question is saying, according to the rate law, an increase in the concentration of H3O has what effect on this reaction? Of course, I can see that increasing the rate of H3O will, of course, increase the rate of the reaction, right? So the answer would be A, because that's just what this equation says. Let's see. Question 3, you guys don't know how to do yet, so we can go over that one later. Ooh, okay, question 4 is a really, really good question. Let me get my little pin ready so that we can go over it. So question 4 is about this related rates idea. I have the rate of decomposition of potassium chlorate, and it's 2.4 times 10 to the negative second moles per second. What is the rate of formation of oxygen at the same time? So I can see that these have different stoichiometric coefficients, so they're going to have different rates. And here is the simplest way of doing this. The rate with respect to a reactant multiplied by 1 over its coefficient. So in other words, 1 over 2 times the rate with respect to KClO3 is going to be equal to 1 over 3 times the rate with respect to oxygen. This is the simplest way of doing this. There was a slide where I tried to spell this out, and you should kind of have memorized how you can translate between this. If I rearrange this equation, then I can see that the rate of O2, which is what I'm being asked to find, is 3/2 the rate of KClO3. And this makes perfect sense. I know that the rate of O2 is going to be bigger than the rate of KClO3 because I get more oxygen being produced. In other words, all I'm saying right here is, hey, for every 2 molecules of KClO3 that disappear, I produce 3 molecules of O2. That's all this equation is saying. We could even get there through stoichiometry. If I wanted to know something about O2, and I am given information about KClO3, KClO3. If I've been given information about KClO3, so I know the rate of KClO3, for example, and I want the rate of O2, I can do stoichiometry, divide by 2 moles of KClO3, gets me 3 moles of O2, and now I have my information in terms of O2. And that's exactly what I'm doing. I'm taking the rate of KClO3 and multiplying it by 3/2, multiplying it by the mole ratio to figure out the rate of O2. So 2.4 times 3/2 is 3.6. 2.4 divided by 2 is 1.2 times 3 is 3.6. So there's my answer. Right away, we can eliminate A, D, and E because we know oxygen has to have a bigger rate because it has a bigger stoichiometric coefficient. It's being produced at a faster rate because I get more of them. I get 3 of them for every 2 KClO3 that is being consumed. So related rates, does that make sense? If you have questions, feel free to jump in at any time. Keep going. Number 5, you can't do that. Number 6, you can't do that. You can't do that yet. Let me look at this. Okay, question 7 is a really good one. So let's try to look at this carefully. So I have a reaction of substance X. Sorry, y'all, I have troubles with my pen being annoying sometimes. Substance X being reacted with substance Y to yield substance Z. And it is saying that I set up this experiment where I have a large excess of substance Y. So it is as if you can see as time goes on, because I have so much Y in the reaction system, it is as if the concentration of Y does not change. In other words, I have Y present to so much greater quantities that X is changing significantly. And even though Y is truly reacting, it is as if it is not changing at all because I have so much of it. So the concentration of Y is not changing at all. So I know that that really the order with respect to Y is 0. The rate for Y does not depend on the concentration of Y. So that's like raising Y to the 0 power just to get 1. So it's 0 order with respect to Y. That's not one of my options. So really this is telling me that I can just ignore Y and focus on X. So let's see what's true about substance X. Well, it looks like I see a curve and I'm trying to figure out what the order is. I'm gonna first focus on half-lives, right? I can maybe figure out what the order on X is based on what the half-life is doing. So how long is the half-life for this reaction on X? Someone unmute themselves, someone brave, unmute themselves and tell me, what is the half-life for X? How many hours? Anybody? Bueller? Nobody? Don't make me call on you.
1 hour.
Okay, I don't know who said that, but that was correct. Yes, the half-life is 1 hour. Was that Mr. Cox? Thank you, Mr. Cox. Excellent. The half-life is 1 hour because I dropped from a concentration of 2 to a 0.2 to 0.1. That's a halving, and that happened in 1 hour. The next half-life would be me dropping from me halving again from 0.1 to 0.05. Oh, that happens in 1 hour, doesn't it? So I have a constant half-life. Someone tell me what order of reaction has a constant half-life. First, second,
First order.
excellent, first order. So the answer is B. I know it's first order with respect to X because the half-life is constant. Okay. All right, yay. Very, very good. Let's do question 8. Can y'all hear my kid playing video games in there? Let me shut the door real quick. Give me 1 second. Hey, Henry. Your time is up on that. Okay? I think it's math time now. So let me go get you ready for my break. Until 10:30. Okay? Okay, you guys, I'm so sorry. Juggling a lot right now. Okay, so it looks like I'm going to use a method of initial rates to maybe find something out for question 8 here. So let's see. I want to know what the rate law is for this reaction. All right, so all I need to do is figure out the exponents, figure out the orders on carbon monoxide and on chlorine gas, and I can use the method of initial rates to do that. So let's work out this method of initial rates problem. So remember, I know that my rate law is K concentration of CO raised to some power times the concentration of Cl2 raised to some other power. What's up, Henry? With the computer. Just do your math worksheets for now, and then I'll come help you, okay? I'm sorry, buddy. You're gonna have to do the worksheets first. Mister, please. Okay, so to find these exponents, I just need to see what changing the concentration does to my rate. These are really difficult to see. That looks like these are both times 10 to the negative 25th power. So from experiment 1 to experiment 2, this is not going to be super helpful for me because it looks like I'm changing 2 things. From experiment 1 to experiment 2, I'm changing the concentration of CO and I'm changing the concentration of Cl2. I'm going to try to pick 2 experiments that that only change one thing. Does that make sense? So let me ignore that for now, and let me look at experiment 1 and experiment 3 to start out with, because it only changes the concentration of Cl2. I can figure this out pretty simply conceptually. I know that from experiment 1 to 3, the concentration of Cl2 doubles. So that is multiplying the concentration by 2 while I'm keeping the concentration of CO the same. What effect does that have on my rate from experiment 1 to experiment 3? Well, 3.9 times 10 to the 25th to 7.8 times 10 to the 25th, you can do the math, that is also a doubling. In other words, there's a 1-to-1 correspondence between how I change the Cl concentration and how my rate changes. I double the Cl concentration and that ends up doubling the rate. So someone tell me what that tells me about this exponent m. What is the exponent? What does the order on Cl2 have to be? Someone unmute themselves or type it in the chat. Is my m going to be a 0? Is it going to be a 1? Is it going to be a 2? What's the exponent on chlorine? If doubling the chlorine doubles the rate, then what power am I raising this to? Anybody?
1.
Excellent. Yeah, the first power. Very, very good. If you really need the mathematics to do that, then you can just write an equation, write a rate law for experiments 1 and experiment 3. For experiment 3, my rate was 7.8 times 10 to the negative 25th. I know that's equal to K times CO to N times, go get a snack, times Cl2 raised to the m, and I know those. It is, and I know those.
I thought you said it was still break time.
No, dude, it's math time. That's why I told you to do the worksheets. I know that CO has a concentration of 0.2. Cl2 in experiment 3 has a concentration of 0.2. And I need to make a ratio, compare that to experiment 1, where the rate is 3.9 times 10 to the negative 25th equals K. My CO concentration is still 0.2, and my chlorine concentration was 0.1. So I can divide these, and I will ultimately get 2 equals, these cancel out, 2 equals 2 raised to the m power. And I know that m has got to equal 1. So I know it's first order with respect to chlorine. Okay? That's how the method of initial rates work. You can either like think through it conceptually, or if you're more of a math person, you can actually write it out, divide the 2 rate laws for the 2 experiments. So now that I know that, I can go back and compare experiments 1 and 2 whenever I'm changing CO, and see what that does to my rate. Now, I can think about this conceptually. I already have thought through the fact that doubling Cl2 should double the rate because it's first order with respect to Cl2. In other words, I know that this is the case.
What is this?
Board games. I know that.
It looks like an R to me.
Oh, I'm sorry. I know that this is a 1 right here. So I know that doubling the Cl2 concentration, multiplying this by 2, should end up multiplying the rate by 2. But here I can see that having dividing the CO concentration by 2 has kept the rate the same. So I know right away that doubling the Cl concentration is trying to double the rate, but having the CO concentration has made the rate stay the same. So I'm able to figure out right away that this n, the exponent on CO, the order with respect to CO, has also got to be a 1. Now, if you're not able to think through that and reason through that mathematically, of course, you can write out your 2 rate laws. Experiment 2, I know that my rate is 3.9 times 10 to the negative 25th. That's going to equal K times my CO concentration 0.1 to the N times 0.2 Cl concentration raised to the first power. I figured that out. Divide that by experiment 1, where the concentration is 3.9 times 10 to the negative 25th equals K times 0.2 to the n times 0.1 to the 1. I divide these out, I'm going to get 1 equals, this is going to be a 1. 0.1 divided by 0.2 is 0.5 raised to the n, and 0.2 divided by 0.1 to the first power is, of course, 2. And so I know that n has got to be a 1 because 0.5 times 2, 0.5 raised to the first power is 0.5 times 2 already gets me 1. So if you can't think through it conceptually, you can always write out the equation. You're always just going to write an equation for one experiment, write an equation for the other experiment, and divide. Okay, so I now know that this is the rate law. It's first order with respect to both of them, or I could say it's second order overall. So it looks like the answer to that question is therefore going to be E. All right, so that's the method of initial rates. This reaction has this rate law. What's going to happen if I decrease the concentration of this substance? Well, the rate depends on the concentration of that substance. So if I decrease its concentration, the rate is going to decrease. A lot of these you guys cannot not do yet. Oh, let's look at number 11. Okay. So here I have a rate law. The rate law for this reaction is NO2 to the power of 2. So I know that it's second order with respect to NO2. And it's saying that I add a small amount of gaseous carbon monoxide to the reaction mixture that was 0.1 molar NO2 and 0.2 molar. Remember, molar is a concentration. So let's think about this. It's asking me about what's going to change and what's going to stay the same. So I think I barely mentioned this in the lecture videos, but K, the rate constant K, that is tied to temperature. So the only way to change the K value is to change the temperature, or I could actually add a catalyst. We'll talk about that later. So I'm not changing the temperature here. So I know that C is a crappy answer. Let's see, D is a crappy answer, B is a crappy answer because those all have K changing. I know K cannot change because the temperature has not changed. So I'm either going to have A or E. And let me see. So I add a small amount of CO. By adding a small amount of, sorry, let me think about this. By adding a small amount of CO, I really haven't changed anything about the concentration of NO2, right? In other words, if I have a closed reaction vessel, maybe that's a 1 liter vessel or something like that, and I have a bunch of NO2 gas particles bouncing around. If I add another gas, that's not going to change how many moles per liter of NO2 I have. So the concentration of NO2 does not change even when I insert more carbon monoxide. If the rate just depends on the concentration of NO2 and I haven't changed that, I'm not going to change the rate at all. So the answer is A. K and the reaction rate remain perfectly the same. Okay. All right. This one would be a method of initial rates. Let's do this one and then we'll move on to maybe some free response questions or the super problem. I'm kind of jumping around here. I'm just trying to find some questions for us to go over and review together just so you guys can be getting some good practice with this. Okay, so let's see. Looks like the first experiments I want to compare are experiments 3 and experiment 1, because I'm always going to look for 2 experiments where one thing has stayed the same and then another thing has changed. That will always be the first thing that I do. So I can see here that I have doubled the rate of X, and excuse me, the concentration of X, and what effect did that have on my rate? Well, you can see that my rate increased by a factor of whatever 1.8 divided by 0.45 is. My rate increased by a factor of 4. So by doubling the concentration of X, I increased my rate by a factor of 4. That means that my rate law is going to look like this: K times X to the N times y to the m. I'm trying to figure out what this exponent on x is right now. If the concentration of x doubled, but my rate quadrupled, someone answer for me. What is the exponent on x, on reactant x? Is it first order, second order, third order, 0th order? Anybody?
The exponent is 2, right?
Excellent. Yes. Very good. The exponent is 2, because if I double the concentration, the only way I can get a quadrupling of the rate is if I raise this to the 2nd power. So the exponent does have to be 2. So I know that this n needs to be a 2. Once again, you can actually, if you can't think through that mathematically, you can actually write it out that and compare the rates and divide, and you'll get the exponent of 2. Okay. And let's see. So there's that. And now I need to look for 2 more experiments where I have kept X the same, but this time I've doubled Y. And this is pretty simple. By doubling Y, the rate has not changed at all. So I know that the rate does not depend on the concentration of y. Doubling y does not change the rate. So I know that the order with respect to y has got to be a 0. So the rate doesn't depend on the concentration of y at all. So here's my rate law. It just depends on the concentration of x squared. All right. What's up, bud?
I'm already done.
You finished those worksheets?
Yeah.
There's something wrong with your math program?
Yeah.
Okay, I'll come fix it for you right now.
And
Oh, no. You guys take a 5-minute break. I'll be right back. All right, dude, let's go. One.
look. Daddy, look.
I see that.
So how's everyone's quarantine?
Very nice.
How do you change the
Wait,
background of your
Killian,
photo?
You'll never know.
hey,
You'll
hold
never
on,
know.
hold on, Sully. Let me have a conversation with you really quick. Killian, my break actually hasn't started, but I'm kind of enjoying just being at home. What about you, bro?
That wasn't funny. I don't know if you were trying to
I
be
mean, you're not funny. I'm not laughing.
Zan, do you feel better?
Yeah, I'm good.
That's good.
He still
Nice.
got corona.
I mean, yeah, there's nothing wrong with Corona. I mean, like,
As long as you treat it.
yo, Eamon, I want to hear your voice, bro. Say something.
Who?
Amen. Say something.
Amen. Amen. Psst. Amen.
Okay, if you guys want to change the picture, you just have to go to the website and change your profile picture, and then it'll change your picture on here.
Thank you.
Everybody, you
Thank
should go
you.
change. You
Did
should go
it.
change your pictures.
I tried to. Why is it not updating?
I think it might take a sec.
Killian,
Yeah.
when's the Nether update coming out?
I have no clue.
Oh, shoot. Here, let me search it up. It just says the first half of 2020.
Zan, answer my call.
On Discord?
Yeah.
Oh, that's my bad.
I'm so sorry, guys. Do y'all want to meet my dog?
Yes.
Yes, sir.
Yes.
Oh my gosh.
Yes.
Yes. Yes, please.
This is Hero.
Oh.
He's a good boy.
Oh.
He does not mind at all that we are home all the time, do you? Hero, what do you want to say? Do you want to say hi? Say hi. Okay. Sorry, I just needed a moment with my pupper.
What breed is he?
He is a German Shepherd Black Lab mix. He is too fat. He needs to go on a diet, but it's hard. Okay. Let's keep going. Okay. He is big boned, right? The vet doesn't get it. Okay, let's do some free response questions, maybe. Okay, we can do part of this one, 1997, number 4. We can't do all of it yet, but you know, the more practice we can get right now, the better. So let's do this one. Some more method of initial rates type thing. So. All right, so determine the order of the reaction with respect to A and B, justify your answer, and then write the rate law, calculate the value of the rate constant, and specify units. Ooh, we haven't talked about that yet, so this will be a good one for us to practice. All right, so in order to do this, I'm gonna have to look for two experiments where something has not changed. And it looks to me like the only option I have are experiment 1 and experiment 2, where B stayed the same, but A tripled. So here I am multiplying the concentration of A by a factor of 3. What did that do to my rate? So these 10 to the negative 4th, 10 to the negative 3rd things make it a little bit tricky to see. So I'm going to write this out, 0.00043. That's the negative 4th, and then 0.0013 would be to the negative 3rd. So real quick, I can make a ratio of those. 0.00043 divided by 0.0013. Oh, whoops, I need to do the other way, don't I? This one is the bigger one. So 0.0013 divided by 0.00043. And I can see that that is pretty much a tripling from here to here. So I can take the time to actually write out, you know, rate equals blah, blah, blah for experiment 1 and 2, divide them, find the exponent on A. But just a quick comparison shows me that by tripling A, I have tripled the rate. And therefore I know that it's first order with respect to A. So far I know this, R equals K. I know that the order on A is 1. And now I need to figure out what the order on B is. To do that, looks like I need to find where B changes. I can either do experiment 1 to 3 or 2 to 3. It does not matter at all now. Oops. I'm going to do experiment 2 to 3. So going from experiment 2 to 3, I can see that A has doubled and B has doubled. I already know that doubling A, because once again, my rate depends on just the concentration of A raised to the first power. I know that doubling A should double the rate. So that should result in a rate change of doubling. So I want to know what doubling B does to the rate. Well, when I double A and double B, it looks like the rate actually changes 1.3 to 5.3. So whatever 5.3 divided by 1.3 is, looks like the rate actually changes by a factor of 4. Well, from changing A, I've already said that if I double A, the rate should double. So what's going to account for the other doubling? In other words, multiplying by 4 is like I've doubled it 2 times. Doubling A accounts for one of the doublings, so doubling B must account for the other doubling. So I know that B must also have an exponent of 1 as well. That was a little bit complicated, so of course you are welcome to actually write 2 equations. So for experiment 3, I can say that the rate is 5.3 times 10 to the negative third, and that equals 1.5 raised to the first power, the concentration of A raised to the first power, times 1.5 raised to the m, because I don't know the concentration on B yet. Divide that by experiment 2, where my rate is 1.3 times 10 to the negative third, equals 0.75 times 0.75 raised to the m. Divide this out, and I will get 4 equals 2 times 2 to the m, and I know that m has got to be 1. So I know it's first order on both of them. So the order with respect to A is 1, order with respect to B is 1. And now to write the rate law, to write the actual full rate law, I need to know what the K value is. So how do I get that? Well, I can just pick any one of these and plug everything in. For example, in experiment 1, I know the concentrations and I know the rate. And I've already said that the rate is equal to K times A to the first times B to the first. So I can plug things in and rearrange and solve for K. In other words, K here is going to be equal to R divided by the concentration of A times the concentration of B. And just pick your favorite experiment. I'm going to pick experiment 1, 4.3 times 10 to the negative fourth. And I'm going to divide that by 0.25 raised to the first power times 0.75 raised to the first power. And that will give me my K value. I'm getting a K of 2.3 times 10 to the 10 to the negative third. So that's my K value. So my final rate law then would be R equals 2.3 times 10 to the negative third times the concentration of A times the concentration of B. That is my rate law. Remember, the point of this differential rate law is to write in an equation that will tell you what the rate is at some concentration of A and B. So there it is. And now I need to try to specify what the units of K have to be. So you can either memorize this, you can memorize the units for K. The overall order of the reaction is second order, right? It's first order with respect to A, first order with respect to B, but second order overall. So you can memorize what the units of K are for a second order reaction, or if you don't like to memorize things, you can actually like figure out what it has to be. So to figure out what it has to be, we can do some math, some algebra, using the same algebraic rules that normal algebra equations follow, just using units. I know the units of R have to be moles per liter, and that's going to have to be equal to whatever the units of K are. That's like my unknown, what I'm trying to find. And I know that A and B are both moles per liter. I'm sorry, the rate has to be moles per liter times seconds, doesn't it? Rate is concentration over time. Concentration is moles per liter. Yeah, maybe we should review that. Rate is always measured in change in concentration over change in time. Concentration has units of moles per liter. So moles per liter divided by seconds, that simplifies to moles over liter seconds. So that will be the unit for rate. So I know that's the unit of R. I don't know the unit of K. I know the unit of A and B, don't I? They are moles per liter, each of them. So I'm going to get moles per liter times moles per liter, and that's going to simplify to moles squared per liters squared. So my K value needs to be something that I can multiply and only have 1 mole left on the top, 1 liter left on the bottom, and seconds on the bottom. If you're not able to think through that, just treat this like an algebraic equation. To solve for K, I'm going to multiply both sides by liters squared and divide both sides by moles squared. Does that make sense? I can treat units here just like any algebraic equation. So when I do that, you're going to get that the units of K equals liters per mole times seconds. Another way of writing that would be liters times moles to the negative first times seconds to the negative first. Another way of writing that would be to recognize that liters per mole is just molarity flipped. So we could write molarity to the negative first, seconds to the negative first. And those are the units of K for a second order overall reaction. All right. Okay. Any questions about that? Okay, part C, determine the initial rate of change of A in experiment 3. So don't be fooled, it's not just this. That rate over there is the rate, excuse me. Oh no, I made a mistake. I just saw the mistake I made. This rate is given to me in minutes. I just reported my K value in seconds, didn't I? Ooh, we have got to read things so carefully. Because they're measuring time in minutes, then my K value is not going to have seconds in it. In other words, rate is not, in this problem, is not going to be molarity per second, but in this problem, my rate is molarity per minute, or moles per liter minutes. So I need to go back and change what I said for K earlier. K is going to be moles to the negative first, liters times moles to the negative first times minutes to the negative first, not seconds. I'm so sorry that I made that mistake. Okay, so going back here, this data is the rate of formation of C. This question is asking me about the rate of change of A. So I can see that C only has a coefficient of 1, A has a coefficient of 2. So I know that the rate of A is going to be twice as big as the rate of C. Does that make sense? In other words, I can say 1 over 2 times the rate of A is going to equal 1 over 1 the rate of C, where I'm putting 1 over those stoichiometric coefficients. And I can multiply this and therefore say that the rate of A is twice the rate of C. That should make perfect sense. For every 1 C I produce, I consume 2 A molecules. So of course A is going to be happening twice as fast, the rate with respect to A. So you multiply this by 2, and you'll get 10.6 times 10 to the negative third. And of course, that's crappy scientific notation. Fix your scientific notation. You get 1.06 times 10 to the negative second. So that's going to be the rate of change of A in experiment 3. Determine the initial value, part D, of B in experiment 4. Well, we have our rate law. We know that R equals K, concentration of A, concentration of B. Well, for experiment 4, we know the rate. We know the concentration of A. We solved for K earlier. So this is just a simple algebra problem. I can figure out what that initial concentration of B must have been. All right. Okay, let us try to find. Hey, Henry, make sure you're working, bud. Who changed their picture to that Corona thing? You guys are a mess. Let's try to find one where we're going to have to find an integrated rate law. Let me see. Sorry, y'all. I'm trying to find a good one. Blah, blah, blah. Okay, this will be a good one for us to talk about real quick. Sorry about that. So I'm looking at free response question from 2014 in the kinetics FRQ little packet. So we have this chemical reaction. Don't get tripped up with big fancy words. You guys will probably never learn about what catalyzed isomerization is. That does not matter at all. It's just this type of reaction is called a catalyzed isomerization. It doesn't really matter. So I'm measuring the half-life of this reaction under various conditions. So it looks like I have some initial pressure of this gas, cis to butene. What's up, Henry Ames?
It's doing that thing where I can't click it.
Okay, just go find something else to do. All right.
Like what?
Go read a book. Okay. So I'm changing the initial pressure, and I'm changing the volume as well. And for the first 3 trials, at least, I'm keeping the temperature the same. And here you can see that I have various half-lives. So the reaction is first order. Explain how the data is consistent with a first order reaction. Well, I know that for a first order reaction, the half-life does not depend at all on concentration, right? They're not giving me concentration values though. They're giving me pressure values. Is that okay? It is okay because I know that I mentioned this in the video in the lecture, so hopefully you were paying attention. For gases, pressure can be a stand-in for amount or for concentration because my ideal gas law, PV equals nRT. Rearrange this, P equals nRT over V. N over V would be moles per liter, right? That's concentration. So I can see that pressure is proportional to concentration. So I can use pressure in a gaseous reaction to stand in for concentration. So this might as well be measuring concentration. And I can see that the half-life does not change as the concentration changes. I have 300 torr of pressure at 2 different volumes, and then I have 2 different volumes at 2 different pressures. That's like me changing the concentration, changing the amount of gas in there, and the half-life stays the same. And I know that that is only true for first order reactions, that the half-life is constant. It doesn't depend on the concentration at all. So that is how we would talk about question A. Question B, calculate the rate constant K for the reaction at 350 Kelvin. So there's this equation, I think it is on your AP equation sheet, that this is only true for first order reactions, only true for first order, that my half-life is equal to 0.693 over K. If you can't remember that 693 number, that is just the natural log of 2. I don't want to take the time to derive why this is the half-life, but it's really kind of simple if you know how log math works. And if you remember that first order reactions use a half-life. Excuse me, first order reactions use natural log. Anyway, I have this equation. I could just plug in the half-life of 100 seconds and rearrange and solve for what K has to be. All right, so I know that this is a first order reaction. Part C, is the initial rate in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. Well, I know that my rate is proportional to I know that my rate is proportional to K times the concentration of my reactant. I'm just going to call it A for now, raised to the first power. So Ms. Young is saying that, that this is on the AP equation sheet, but they don't tell you what it is, I think. They don't tell you it's for first order reactions only. So you have to be familiar with that and know that. Yes, thank you, Ms. Young. So I know that this is true for my rate, raised to the first power because it's a first order reaction. So they're asking me, is the initial rate of reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Well, let's think about this. What's different between trial 1 and trial 2? The volume is the same, but the pressure is increased. So if the volume is the same, let me make this to where you can actually read it. If the volume is the same in both trials, but the pressure has gone up from trial 1 to trial 2, then the temperature has stayed the same. The only explanation for that is that trial 2 has more moles. Therefore, the concentration is bigger. Number of moles per volume is larger because I have the same volume, larger pressure, so I must have increased the number of moles. So I can see that the rate depends directly on the concentration or the amount or the number of moles that I have. So the initial rate of reaction in trial 1 is then going to be less than it is in trial 2 because trial 2 has a higher pressure at the same volume, and therefore the rate has to be higher in trial 2. What if it had asked me to compare like trial 1 and trial 3 or something? Well, those are at the same pressure, but the volume is different. So I know that when my volume goes up, the pressure typically wants to go down. But because the pressure has stayed the same from 1 to 3, even though I've increased the volume, the only way for my pressure to stay the same if I've increased the volume is to increase the number of moles. So this has to have a higher concentration. Okay. Another way of thinking through that is just that the number of moles is proportional to pressure times volume, and this has a larger pressure times volume, so it has to have a larger number of moles of gas. Okay, we cannot answer question D yet. I really want to try to find a question here in our last 20 minutes that is going to help us with integrated rate laws. So I'm going to go over here to this practice quiz. Question 1 is going to be a really good question for us to look at. So here I have first order reactions. I know it's first order because the natural log versus time has made straight lines. Which two,
Daddy,
what's up, Henry Ames?
how long did you say I had to do lecture?
Until 11 o'clock. So you have about 20 more minutes, okay? Good job, Ben.
I think I'll finish the level because I'm on the second half and 20 more minutes is a long minutes.
That's awesome, buddy. I'm proud of you.
Go.
Which two represents experiments done at the same temperature? So how does temperature relate to all of this? Does anyone remember what I've said about temperature and how it relates to these reaction rates? It relates to something in our rate law. Anyone know? Yes, Ms. Skoma is correct in the chat. She says it relates to K. And K is, of course, the slope. So which two lines have the same slope? It's clearly A and B. So A and B there have the same slope. So they must be at the same temperature because they have the same K value, where K value is the slope. What accounts for the differences in these lines? Well, looks like they have different y-intercepts, don't they? What's the y-intercept of this? It's the natural log of the initial concentration. So they must have different initial concentrations. Part B, which two lines represent experiments done with the same starting concentration but at different temperatures? That's got to be A and C, right? because once again, they have the same y-intercept basically. So the y-intercept is the natural log of the initial concentration. They must have the same initial concentration, but C is much steeper than A, so they must be at different temperatures. We can't do questions 2 and 3 yet, so let's save that. Okay, question 4. You know what, I think this will be the last one that we do. So here I have a reaction. I don't tell you what the reaction is, but we can assume that it's a reaction that has one reactant. And I've given you concentration versus time data for that reactant. I know it's a reactant because its concentration is going down as time goes on. I want to write the complete integrated rate law for this reaction. So remember, the first thing I want to do when I have concentration time data is see if I can figure out something about the half-life. That might help me figure out what order the reaction is. So a half-life will be when this drops to 0.05, and that's not a precise data point. I know it's going to occur though between here and here. So maybe I'm thinking right now that this first half-life, that the first half-life is maybe about, so it's gonna get cut in half to 0.005 between here and here. So I don't know, we'll call that about 1400 seconds, assuming that time is in seconds here. So let's see how long the second halving takes, the second half-life. That would be when it gets cut to 0.005 to 0.0025, and that looks like it occurs down here. And I can see that that's going to be at about what, 4,800 seconds total. So my first half-life happened at 1,400 seconds. So that's a change of 1,400 seconds. My second half-life occurred at about 4,800 seconds. That's a change from the first half-life to the second. That's a change of 3,400 seconds. So I'm not certain because I don't have exact data points, but it seems to me like the half-lives are getting longer. What type of reaction has half-lives that get longer? Anyone know? First order, second order, or zeroth order? Which one has half-lives that get longer? You have a 33% chance of getting the answer correct. Second order, Miss Young, that is correct. Second order reactions have longer half-lives. So I'm already thinking that it's second order. So that's like my hypothesis maybe. And to check to see really, I would need to go into my graphing calculator and graph this data. I need to, in list 1 of my graphing calculator, I need to put time. In list 2, I'm gonna put concentration. In list 3, I'm gonna put natural log of concentration. And list 4, I'm going to put 1 over the concentration. So everyone should practice doing that. You guys need to be able to do this very quickly, because if this was a free response question, it's, I think, pretty easy points. So I would recommend practicing this on your graphing calculator as much as you can. So to do this, I'm going to go to Stat, Edit on my calculator. I have lists. I can punch in the time values in list number 1. I know that you guys have never had a better, more thrilling internet experience in your lives than watching me type numbers into my calculator. I know that's super fun for you. And then in list 2, I'm going to type the concentration, 0.01, 0.00625, 0.00476, 0.00476. Okay, and then in list 3, I want to plug in the natural log of all that crap. I don't have to go in individually. I was trying to say this to you in the video lecture. I can just go up to list 3, to the top, to the heading, and I can type in equals natural log of list 2. Just like that. I don't know if y'all can see that. And it will generate those values for me. Do the same thing for list 4, equals 1 over 1 divided by list 2, because list 2 is my concentrations. Okay, and now I just need to run linear regressions. To do this, I'm going to go to Stat, Calc, LinReg. I'm going to check out list 1 and list 2. That gives me pretty crappy R values, like 0.84. So that's not very good. Stat, Calc, LinReg, check list 1 and list 3. List 3 was the natural log values. That's a little bit better. I'm getting an R value of 0.95. And then Stat, Calc, LinReg, list 1 and list 4. And that gives me the best R values. And that's exactly what I thought, right? 1 over concentration data, that being a straight line, is indicative of a second order reaction. And the half-lives are getting longer, which is indicative of a second order reaction. So I know that, the reaction must be second order. So the integrated rate law is therefore going to be 1 over the concentration of C4H6 is going to equal K, where K is going to be the slope of that line, which I can get from my LinReg. I'm getting a slope of 0.061 times time plus 1 over the initial concentration, C4H6 sub 0. Now what I have is a mathematical tool that will help me for any initial concentration and any time will help me find 1 over the concentration. And then at what time will the concentration be? Half. So all I would have to do is plug in 0.005 here and plug in the initial concentration here and solve for that T value. Or I can recognize that's a half-life and I can memorize the equation for a half-life maybe. Okay, that was all kind of a rush and a blur, but hopefully it wasn't too overwhelming for you. Hopefully you guys are getting the hang of all this stuff. There's a lot for you to keep straight in your brains, from differential to integrated rate laws, different orders, first, second, zeroth, and the methods for determining the rate laws, method of initial rates, which we did several examples of for differential, and the method of running a linear regression when you have time and concentration data for integrated rate laws. And I want you guys to know that they're related to each other. So I've just found out that this is second order. So I could write the differential rate law as well. R equals K times the concentration of C4H6 raised to the second power. I could write, once I know the integrated rate law, I can write the integral. Once I know the integrated rate law, I could write the differential rate law. They have the same Ks. The Ks are the same for them. So 0.061 here in this example. You need to know the different half-lives and the different half-life patterns for the different orders of the reactions. You need to know the different K units for them. So that cheat sheet that you have that I uploaded onto my haiku class is going to be really helpful for you. You have the PowerPoint, all this stuff. Are there any final questions before I let you go not do chemistry for a week and a half? Anything at all from anybody? You guys surviving? Mr. Sanders suggested that I make a 90s playlist for you guys because he had heard that I made a 90s playlist for one of my—
Did you just say my last name is Sanders?
I'm so sorry. I haven't seen y'all's faces in so long. It's like, who even are you? Who are we in this age of internet communication? Mr. Sanford, I'm so sorry.
Thank you.
Anyway, I can post that playlist. Sometimes you just need some 90s music. Am I right? Yes, I am. Any questions? I don't expect you all to work over spring break. I do expect you to like maybe think about chemistry to prepare for your AP exam. Any statements? Oh, that's good news, Miss Majid. Thank you for helping us end on a positive note. Yay. It was bound to happen. So y'all need to stay in y'all's houses. Y'all need to don't shake hands. Y'all need to wash hands. Stay in your houses, social distance, listen to 90s tunes. Y'all will be all right. Let me know if you need anything, and I guess I'll just see you guys after the break sometime, okay? Everyone, last night I did post a little message about your grades. Because this last test was so unconventional, I just gave you all A's on your test, unless it was going to make like a really big difference in your grade, unless you were like just on the cusp. Then I needed to know if it made a difference, like what kind of A you made on the exam. So, for example, if you had like an 88 on the in the class, and like getting a 97 on the test would have bumped you over to an A, then I did take the time to actually grade your test to see if you got that high of an A value. Does that make sense? I thought that was pretty fair. Like, in other words, if your exam grade was not going to change your grade, I didn't take the time to grade it. I just gave you an A. That's mostly for my benefit, actually, because these past few days have been really overwhelming and exhausting for me. Okay, so please let me know. Reach out if you need anything. Do not go to any large gatherings in small spaces, gentlemen. All right, I will see you guys after the break. Please try to think about AP chemistry at some point, and we'll get started with this kinetics unit. We're about 3/4 of the way through the kinetics unit, really. We'll get started back with it after spring break, and then we only have 2 units left after that, so yay. Thank you guys. Have a great break, and stay safe and stay healthy. Bye.